Alrighty. Are we working now? Should be. I don't see why we wouldn't be. Aha! It's live. Cool. Alrighty, so welcome to everyone who's going to join me tonight. Give this a crack. It's 8:50 p.m. at the moment, so the 3-hour exam would mean that we'd finish at around 10 to 12. We'll see how we go with this one though, but no promises that we'll finish this one. Hope you joined the music in the background. I'm just trying to put something on that I'm not going to get taken down for. If it does, I'll have to do this whole thing again, and it'll be another 3 hours. It's gonna be pretty harsh. But I just want to start by saying that as a school teacher myself, it's really heartbreaking to see what's happening with everyone and what everyone's going through at the moment, especially in New South Wales. That's the state I'm from, and we just went into lockdown. As of yesterday, as of time of recording, and it's just not nice. And especially coming up to such an important time in the year, kind of like an ongoing, not an ongoing, but like a sort of, your first steps into adulthood is like these big exams, and it sucks for a lot of young people out there who haven't got the opportunity to have a go at these exams. I'm sure there's some people out there who are cheering that they don't have to do them, but I know a lot of people are really trying their guts out to do the best that they can, and it's just a really crappy time all around. So I'm hoping that this video, and consequently a few more, depending on if I've got the time or not, coming up, help. And that's all these are about. It's just another perspective, another voice, for you guys to to listen to, and to for you guys to listen to, and for you guys to just I don't know how to finish that really, but anyway. So this is the Northern Beaches Secondary College. I'm sorry, I just got a little bit of cold at the moment, but nonetheless, yeah. So it's the Manly campus, Northern Beaches. It's the last year. It's their trial exam from last year. Now, it's quite cool. I've actually found this, and I found a bunch of trials as well. But yeah, we're gonna have a go at this one, see what we can do. Okay. Write your student exam number in the boxes. I don't have a student exam number, so I guess we'll just do the classic 1, 2, 3, 4, 5, 6, 7, 8. Okay, and we shall move on from there, I suspect. Now, when you go to sit your exam, I 100% recommend that you do the multiple choice last. Never start with the multiple choice, because if you do run out of time, it's always a good thing to come back to, just to guess a few problems. Now, we're in the situation where we don't have to, rush to finish our exam. So we can not ignore the multiple choice, but we can do the multiple choice first, and we can we'll do it first, and see how we go with these ones. But in a normal exam situation, I would recommend doing the multiple choice last. Alright, so let's have a look. So about 15 minutes. It's about 5 to 9. So let's see how long it takes. Alright, given that log base 3 of 5 is equal to 1.46 and log base 3 of 2 is equal to 0.63, evaluate log 3 of 100. Now, there are some calculators where you can actually put this into your calculator and get an answer, but we're going to use a few log laws to do this, okay? Because the majority of calculators that you're going to have are not going to be able to put this logarithm straight in. So this is what we're trying to evaluate. So I'm actually going to work with that. I'm going to work backwards. So log 3 of 100 is equal to... Now, we can break up log 3 of 100 to be log 3 of 10 to the power of 2, okay? And using our log laws that we know, the power on the inside, well, it can just come on the outside like this, okay? This is one of our log laws, like that. Now, coincidentally, we've got 10 on the inside here, and we've got 5 and 2. Now, 10 is made up of the factors of 5 and 2, so we can rewrite this as 2 log 3 of 5 times 2, like that, okay? Pretty straightforward. Now, using our log laws again, now there's another log law for when we have the multiple, or the product of two numbers on the inside of a log, okay? This becomes 2 log base 3, or 2 lots of log base 3 of 5 plus log base 3 of 2, okay? And just as a little reminder on why that works is, remember, logarithms are like the opposites of, or the inverses of exponentials. So if you have 3 to the power of 5 times 3 to the power of 2, what do you do with the powers? You add them together, and so that's why we can break it up like this. So from here, we know that log 3 of 5 is about 1.46. So 1.46. And log 3 of 2 is about 0.63. So 0.63. Okay, and we're just going to plug that straight into our calculator and get an answer. So do calculator. Put it in, get 2. 2 lots of 1.46 plus 0.63. SD, and we get 4.18 as our solution. So there we go. First one done. Hope you like the tunes, by the way. I just picked some Nintendo music to do. Just something a bit different. Something definitely a bit different. Alright. Let's have a look at question 2. Alright, another logarithm. This time we've got a little bit different. We've got, given f of x is equal to log base e of x minus 3 and g of x is equal to x plus 4, the domain of f of g of x is... So, the way I do this, if we have a look at the function, f of g of x, okay, if we think of a function, f of x, basically means wherever I see an x, so regardless, this is just on the aside, wherever I see an x, okay, I'll replace it with the number that's on the inside here. So for example, if I replace this with a 3, wherever I see an x over in this side, I replace it with the thing on the inside of the brackets, okay, regardless of what is on the inside, okay. So if I've got g of x on the inside here, it's basically saying whatever g of x is, we're going to put that on the inside, okay? So f of g of x is the same as having f of, well, the function g of x, in this case, x plus 4, okay? Now the function we've got is this one over here. So f of x of log, or f of x is log base e of x minus 3. Okay, now if we substitute our value into that, so we're replacing all of our x's, remember? We're replacing all of our x's in our original, so our original function, our f of x function, is equal to log base e of x minus 3. We're replacing our x's with x plus 4. So it's going to become, whoops, it's going to become log base e of, now replacing x with x plus 4, so x plus 4 minus 3. Okay, and simplifying that, our function becomes log base e of x plus 1. Now we haven't actually finished the question, because the question is, well, what's the domain of this? Okay, what are the values that make this work? Now, we know that the domain of any function is basically the numbers that work, okay? So what numbers make this work? Or in other words, what are the numbers that don't make this work? And we want the opposites, okay? It's like the way I like to think of it. So the things that can't go into this, well, it's a logarithm. So a logarithm, so log cannot be equal to 0, okay? And a log cannot be less than less than or equal to 0 as well. So it can't be negative, essentially, or 0. So our solution in this case must be, well, when this inside, okay, when x plus 1 is greater than 0. Okay, so its values when it's bigger than 0. So just rearranging and solving this equation, we get when x is greater than negative 1. Okay, and that's our solution there. And that's it. All right, next question. The sample space of a fair die is rolled. Okay, well, the of a rolled die is 1, 2, 3, 4, 5, 6. Each outcome is equally likely. Okay. For which pair of events A and B are A and B independent? So independence basically meaning that they've got nothing in common. Okay, they're independent of each other. So let's have a look. Okay, this first one, A and B. Well, 2 and 3. And actually, am I thinking of independence or am I thinking of mutual exclusivity? I believe mutually exclusive is when they have nothing in common. Independence is when the probabilities are the same. So when A and B are independent, so we're looking for the probabilities that are different. Okay. So the probability of A in this case, in this one, is going to be 2 out of 6, whereas the probability of B is going to be equal to 4 out of 6. So depending on which group I pick, the probability changes, is my understanding. Hang on, I'm getting a little confused. Probability of A and B is equal to the probability of A times the probability of B. Is when it's mutually exclusive. Is when it's independent, sorry. So it's basically when this thing is equal, when this guy is equal. So when the probability of A and B is equal to the probability of A times the probability of B. Okay, that makes a bit more sense. Definitely thinking of mutually exclusivity. Don't do that. Okay, we want independence. So independence is when the combination, okay, is the same. So they're independent if the combination of the two is the same as the probability of them separate, essentially. So we've got A and B. So we've got 1, 2, and then we've got 1, 2. So two are in common. So the probability of A and B in this one is equal to 2 out of 6. The probability of A times the probability of B is equal to 2 out of 6 times 4 out of 6, which, well, we know is these aren't the same. Okay, these aren't the same values. Okay, the probability of A and B, well, in this case is 0, and we know this is not going to be equal to 3 out of 6 times 3 out of 6, okay? Because 0 just, that doesn't work. Okay, looking at C. C, okay, we've got the 3 in common, so the probability of A and B is 1 in 6. Okay, and is that equal to 3 out of 6 times 3 out of 6? Well, 3 out of 6 times 3 out of 6 is the same as half times a half, which is a quarter, so these are not true whatsoever. And finally, we've got 1, 3, and 5, and 3 and 6. So the probability of A and B is equal to what? So we've got the 1 in common, so 1 out of 6. Probability of A times the probability of B is equal to, well, we've got 3 out of 6 for the first bit, we've got 2 out of 6 for the second bit. 3 out of 6 times 2 out of 6 is the same as 5 out of 6 out of 36, which is the same as 1/6. So that is our answer for that one. Okay, so we're looking for when they're the same, and then that was, in that case, that was the only one that was the same. All right. The function f of x has derivative f dash of x is equal to 8 sine 4x, and f of pi on 4 is equal to 1. Which of the following is f of x? So we've got a derivative and we've got a point makes this derivative true. So we're looking for the original function. So we've given a derivative, looking for the original function, we're going to be integrating this thing. So f of x, so the original function is going to be equal to the integral of the derivative of the function, the derivative of the function. So this is equal to, okay, the integral of 8 sine 4x dx. Okay. It's only an indefinite integral because we haven't been told any bounds about this. So let's solve this. Okay, and from here, so recall that when we integrate any function of a function, so we've got a little function on the inside of a bigger function here. Okay, what I could do is I could pull this 8 out the front here. Okay, and we've got sine of 4x on the inside, but I'm just going to leave it on the inside for now because it's going to simplify a little bit. Okay, but when we have a function like this, the function of a function that we're trying to integrate, so sine of 4x, we're going to pull the derivative of the inside, and we're going to write 1 over that. So it's essentially 1 over, okay, the derivative inside, so the derivative of 4x is just 4, so it's 1 over 4, and then the derivative of the outside, so the derivative of 8 sine 4x is, sorry, not the derivative, the integral of 8 sine 4x, which is in this case going to be negative 8, so the 8's already there, negative cos 4x, okay, so that stays as it is. Okay, so putting this together, we get our function to be negative 2 cos 4x, and of course, the constant of integration. Now we know that at the point pi on 4 and 1, which is what this is talking about up here, okay, because the function value, remember this is our x value on the inside here, and this is the value that's producing, or the y value of the function. So that pi over 1, okay, is a point that this function goes through. So substituting it into my function. So if this is what I know so far, okay, we're trying to find what c is. So what is c? Okay, so substituting the point in, okay, what do we get? So let's do it. Oops, that was an accident. Okay, so substituting that point in, we get 1 is equal to negative 2 cos of 4 lots of pi on 4, so it's just going to become pi when we simplify it, plus c. Okay, now simplifying that right hand side, so it's going to be minus 2 cos of pi plus c. Now cos of pi, think back to your exact values. Cos of pi is going to be negative 1, so we end up with 1 is equal to, well, it's going to be negative, am I right? Cos of pi is negative 1, isn't it? Why do I feel like I'm wrong? I'm looking at the solution that they've provided, and I don't actually agree with it, because that negative 2 we still have out the front, because it hasn't changed yet. Yeah, okay, they've done something really weird in their solution. Okay, I don't actually agree with any of these answers. So if I was to finish this off, so negative 2 times negative 1, because cos pi is negative 1, plus c, we end up with 1 is equal to 2 plus c, so c is equal to negative 1. Okay, yeah, that makes sense. Yeah, no, they've just made a little mistake in their solutions, which I'm just cross-referencing as I go, just to make sure that I'm not making any mistakes, or too many mistakes, I should say. Yeah, so basically we come to c is equal to -1, so my function, therefore my function f of x is equal to, so it's going to be -2 cos of 4x minus 1, okay, which is this guy up here. All right, we've got question 5. Let f of x be a differentiable function such that the domain is from -infinity to infinity. The first derivative of -2 is, or at -2 is 0, and the second derivative is greater than 0 if x is not equal to -2. Alrighty. So, at x is equal to -2, the graph of y of f of x has what? Is it a horizontal point of inflection, a maximum turning point, a minimum turning point, or a vertical asymptote? Well, from what we know, okay, we know that the derivative of the function is greater than 0, okay, for every point other than at -2. So that means at -2, okay, it's either going to be less than 0, which doesn't make sense because there's at no other point it hits 0, so it would have to be equal to 0. So at x is equal to -2, f dash of x is equal to 0. So it's some form of stationary point, okay, and I think we've pretty much gathered that. Or it doesn't exist, but we know that it exists at a value, so that we can cross out the vertical asymptote straight up. Now the derivative value at -2 is 0, so that also helps us in confirming that the fact that it is equal to 0. Now, because the first derivative is also greater than 0 at every single point, that means that the gradient of the function is always going to be positive, okay? So the situations we could possibly have is we could have a stationary point sits like this. Okay, we could have a stationary point that sits like this, or we could have a stationary point that sits like this or like this. Okay. Now, if we look at the derivatives, the gradients, it's positive in this direction and negative in this direction. So it's not always greater than 0 in this case. Okay, and it's a similar argument for this one as well. So it's negative going that way, but then positive going that way. So it's not always greater than 0. Now, it's got to be out of these other two, okay? So it's going up in this direction, and then it goes flat, okay? It goes flat there, and then it keeps going up in this direction. So it looks like it's a horizontal point of inflection, okay? Which is what part A is. Now, obviously, it's not this type of one. Even though this is a horizontal point of inflection, if we were actually to sketch this thing, it would look more like the above one, because the gradients or the slope is increasing, it's going up. The function is going up as we go from left to right. Okay. Okay. The graph of y of f of x undergoes a vertical dilation by a factor of a, followed by a horizontal translation of b units to the right, and is then reflected in the x-axis. The resulting graph is, okay, and it's one of these. Oh, excuse me. All right. So y is equal to f of x. So if we have a function, anything to do with the vertical that is moving or dilating, we are changing the y. So y over a is a dilation. Y minus a is a translation in the vertical, okay? X over b is a dilation in the horizontal. X minus b is a translation in the vertical, okay? So basically, we're looking at either changing the y or the x depending on what type of dilation or translation we're doing. Okay, so these ones are my vertical ones. These ones here are my horizontal ones. So essentially, I'm putting a number in front of the letter or changing the letter around based on what I want. So I've been told it undergoes a vertical dilation of factor A. that means we're replacing the y with y over the factor of my vertical dilation, being a in this case, okay? I'm going to rearrange this in a moment, so just bear with me for now. Followed by a horizontal translation of b units to the right, okay? So if we're going to the right, that means we're changing it. We're changing x, okay? So x to x minus the amount we're translating to the right. This is going to be f of x minus b in this case. Now, one last step is we just need to move the a to the other side, and that gives us y is equal to a, lots of f of x minus b, just like that. It would also help if you actually write the correct... Oh, and it's reflected in the x-axis. So reflection in the x-axis basically means all my positive values, okay, in the y are going to become negative in the y, okay? So my y values are changing, so that's also like changing the y to a negative y, which is putting that negative out the front. So it's going to be that guy there. Okay? Helps if you finish reading the question first and then doing that answer, but yeah. So a reflection in the x-axis means we're replacing the y with negative y. Okay, the dilation, vertical dilation of factor a means we're replacing y with y over a. And a horizontal translation of b means we're replacing the x with x over b. Okay, the area of the curve y is equal to 2 cos x, as shown below, is approximated by two rectangles. What is the value, or the value of the approximation is? Okay, so rectangle formula. Okay, we need a distance or a length along here, and we need a height up here. Okay, we need a height and we need a length. Okay, so my length is pi on 6, and pi on 6 for both of these ones. So area 1 is equal to pi on 6 times, and well, we need to know what this value is in here. Okay, well, we know it's touching the curve, so I can substitute pi on 6 into this equation here. It's going to substitute, and it's going to give me a value. So y is equal to 2 cos pi on 6, okay, which is equal to 2 lots of, or cos of pi on 6 is, now let me think back to my exact values. So cos of 0 is 1, so that means cos of pi on 6 is going to be root 3 on 2. So it's equal to root 3, okay? So my first area is going to be root 3 pi on 6. Now area 2 is this area in here, okay? Again, it's pi on 6 units long, and how many units wide, or how many units tall in this case? Again, we can substitute our function value into this equation here. So y is equal to 2 cos of pi on 3, okay? And cos of pi on 3 is just equal to a half, so my y value here is equal to 1, okay? So area 2 in this case is equal to just pi on 6. So my total area, all I've got to do in this case is just add up my areas. So it's area 1 plus area 2. So this is root 3 pi on 6 plus pi on 6, which gives us root 3 pi plus pi on 6. And factorizing it, well, common factor to both of these is pi. So pi root 3 plus 1, okay, because we have 1 there, on 6, which is that 1 there. Excuse me. Okay, and that's our final answer there. Alrighty, a sequence and series questions, and it looks like we have what type of series is it? Hopefully you picked up on a geometric series, because it has a common ratio, and our ratio in this case is 3 because we're multiplying it by 3 in each step. My A value, my starting value, is equal to, in this case it is going to be 5. Now, which of the following is correct, or is the correct value, Sn, for the series given below? Okay. So all we've got to do is we've got to work out, well, what position or what number positioned this value is here. Okay, so whereabouts in the sequence does this number occur? And once we've worked that out, we can then substitute the number in and get an answer. Or we can put a number in. So we need to work out what that is so we can do S of n. Okay. So how do we do this? Well, we're going to use our Tn formula. So basically the formula is T, so the tth term, the Tnth term, I guess you would say, is equal to A r to the n minus 1. Okay, so we're going to substitute in what we know. Okay, and this is the sum, I believe, for this one. Okay, so this is the sum of these. No, not sum, this is the position that the term is. Okay, so if we knew what n was, this would determine what position the term is, or what number is in that position. So if I knew, say, if I wanted to find what number that was in the 5th position, okay, I've got my A is 5, my R is 3, and I would substitute n is 5 into this, and it would produce the number that's the case. So let's work backwards then. So we know what T of n is in this case. We know Tn is equal to 98415. Okay, and this should help us find our n value here. So substituting it in, 98415 is equal to, well, I know what my A value is, it's 5, times R, which is 3, and to the n minus 1, which I don't know yet. Okay, now let's simplify this. So I'm going to divide both sides by 5. So 98415 divided by 5 is equal to 19683, and that's going to be equal to 3 to the n minus 1. Now to get the n minus 1 out of that exponent, we're going to take a logarithm of both sides, and the logarithm we're going to take is going to be the log of base 3. Okay, just like this. So log 3 of 3 to the n minus 1. Now using that power of a logarithm rule that we used before, this is the same as n minus 1, lots of log 3 of 3. 19683 on this side. Now log 3 of 3 just equal to 1, because it's essentially asking myself 3 to the power of what is equal to 3? Well, that's 1, and then n minus 1 times 1 is just n minus 1. Okay, then finally I just need to add 1. So n is going to be equal to log base 3 of 19683 plus 1. Okay, so I'm moving that minus 1 to the other side. Now to input this into our calculator, we need to do a change of base, okay, because our calculator can't do these logarithms. So pick a new base. Now our calculators can do log base 10, so we'll use that as our new base. 19683 goes on the top, and then our old base goes in the bottom, and then the plus 1 on the bottom, or next to it like that. Okay, let's substitute this in. Now the default log button on your calculator, if you're using Casio 82, will be log base 10, but you can use ln as well. It doesn't actually change as long as the base is the same. So don't use a combination of the two. Make sure you're using one or the other. So log of 19683 over log of 3. And watch what happens here. If we do the plus 1, we get a nice even number, 10. So coming back up to this original equation now, or this original, I guess we could call it shopping list, we know that our n value is equal to 10. So we know what that is now. Now we can work out what the sum of all of this stuff is, okay? Now the formula for the sum, I believe, is a to the r, I've got to remember this. I think it's Rn minus 1 over R to the n minus 1. I'm just going to double check this because I can't remember off the top of my head. But keep in mind that you do have a reference sheet that do have these formulas. They do have all of the sequence and series formulas on there. Okay. And you can recall them and use them at any time that you want. And in fact, that is the formula. So good on my memory for remembering that. So this value, what's it equal to? well, 5 lots of, well, it's r, so 3 to the 10 minus 1 over, now our r value again is 3 to the 10 minus 1 again. Okay, now let's plug this into our calculator. Okay, so we go 5, we'll put the fraction in first, 5 lots of 3 to the 10. Okay, minus 1. Oops, make sure you close the bracket off properly, otherwise you'll end up with a syntax error. 3 to the 10 plus 1 on the end. Not plus 1, that was from the old thing. Minus 1 down the bottom on the end. And we get something that doesn't look right. I know what I've done. I put the minus 1 up the top there. So just be careful when, especially if you get an answer like that that doesn't make a lot of sense, check that you've put everything in right. That also doesn't make sense. I don't think that should be right. I'm just going to double check that formula again. 5, 3, 10. Oh, because it's not 3. Okay, little mistake. It's only 3 on the bottom. It's not 3 to the power of n. It's just r minus 1, not r to the n minus 1. That would possibly make a huge difference, and it does. Okay, so we're expecting these numbers to add up to something pretty big, because if you think about it, if my last number is 98,415 and I'm adding other numbers onto it, I shouldn't get something that's only, what do I get, 5? Like, that doesn't make any sense. So yeah, just keep that in mind when you're doing that. Okay, anyway, oh, well, answer 157620. Yeah, there it is there. So happy with that. Okay, just get a quick drink. Because I can actually feel my throat starting to go, which is not good. Much better. Ooh, I hate trig graphs, and I think everyone does, but we'll get through it. Alrighty, so we've got question 9. The correct graph of y is equal to negative 2 sine 2x plus pi on 3 is equal off of 0 to 2 pi. Which one of these? So, what can we rule out immediately? Well, So, looking at this thing, just judging from this thing, okay. Excuse me. If I was to have my original sine function right, so let's go this. So I'm just going to use this one here. So basically, it's going to look something. Okay, I'm not saying I'm a Picasso or anything. Oh, it's going up by pi and 3s. Actually, that's really annoying. Okay, so our original sine function is going to look something like this. Yeah. Probably not that, because it should be from 0 to pi, it's going to be that. Yeah. Because we're going to have... Hang on, let me think. From 0 to 2 pi, it's only one cycle, isn't it? So it's actually going to be even bigger than that. It's going to be like... Cowabunga, dude. Something like this. And if I actually do my ones properly, so 1, 1, 1, like that. So halfway is going to be like there, halfway is going to be like there. So it's actually going to look something like this. Okay. So in relation to these, and I'm only just drawing this so I sort of have a basis to start on. But my original function is going to look something like that. So from 0 to 2 pi, it's a single cycle, okay? So what's happening in my function to get it to look like the thing that it is here? Okay, well, let's start off by looking at this thing here, okay? So we've replaced the x with 2x. So that's a dilation. It's a horizontal dilation of a factor of 2. So doing a horizontal dilation means I'm going to either stretch it inwards or outwards towards a y-axis, okay? And I'm going to be pushing it in and essentially squishing it in this case by a factor of 2, okay? So remembering that x over a would be like dragging this thing out. So ax, or in this case 2x, means I'm pushing it in. So I should be able to fit 2 of these sine cycles, okay, within the confines of my domain, which is 0 and 2 pi. So I can see that in all these cases too. So if you have a look, so from here to here is 1, and then another one is 2. From here to here is 1, and another one is 2. From here to here is 1, and ooh. Okay, well we can rule out, is that right? Oh no, because I put it in the wrong spot. From here to here is 1, and then that's another one there. Okay, and then from here to here is another one, and another one is there. So I've 100% can fit 2 of these sine waves within all my domains. Just there. That's better. So yeah, I can 100% fit 2 of these sine waves in all my domains, which is fine. Okay, so we're happy with that. Now the plus pi on 3 basically is going to shift my whole function to the left by pi on 3. So that means that let's restrict. Let's take my function that I've drawn and let's essentially halve it and see what happens. So halving this, so this is originally where pi on 2 was, and this is pi. This would have been 3 pi on 2, and this is 2 pi. So this 2x is basically saying halve everything, okay? So this pi on 2 is essentially going to become pi on 4. Okay, so my new point comes up here. This point becomes pi on 2. So my new halfway is down there. And then we get pi on 3 down here, and then like that. And so that 2x, what that's doing is it's pushing all of that red that I've got drawn currently into that position where that blue is. So I'll zoom in a bit. So see where my red was, okay, it's pushing it into where the blue is now. So that's what that 2x in front of, well, that's what the 2 in front of the x is doing. It's compressing that red into that blue. But because the domain is from 0 to 2 pi, what we need to do is we need to actually extend this and continue this pattern going. Okay, so again, my dots that I've got carrying over are going to be where my halfway points are. Okay, let's put my values in like this, and we'll connect them up and keep it going. So just to quickly recap, so red is y is equal to sine x, blue is y is equal to sine of 2x, okay? And we eventually want to get it to look like this, okay? Which is going to be pretty tricky, but we'll get there, and we will, okay? It's just a bit of a longer question, and this is why I suggest leaving the multiple choice to the end, because for me personally, these trig graphs take a while to work out, because it just, especially because of the transformations. And there are a few tricks that you can quickly see, like, you know, knowing that it's like, okay, got to compress it by 2, -2, front's going to flip it and stretch it out, etc., etc. But just knowing some of those tricks, and if you do run out of time, just being able to guess something is just a really crucial tool. Okay, next color is going to be green. So my next value is, well, we've got plus pi on 3 here. So we're adding pi on 3. So we're going to be shifting this whole function to the left, okay? Because we're adding pi on 3. So we're shifting this whole function to the left. So basically every value is going to be moving across by the same factor, okay? So everything's moving across by the same factor. So if I can work out what one of them are going to move by, I can work out what they're all going to move by. So pi on 4, well, we could start with my 0, but 0 is all the way over there. I don't really want to bother. Pi on 4, take away pi on 3 is going to be 3 pi on 12, take away 4 pi on 12. I hope I've done that right. Yep. So which is negative pi on 12, okay? So basically this point here, okay, that point there that I've just drawn my arrow, is going to shift across to negative pi on 12, which is going to be somewhere over there. Okay, so effectively every single point is going to be moving across by that same factor. Okay, now let's do another number just so we can see what our gap is going to look like. So our next value is going to be the, so I'll get rid of this green because I don't want it to double up. Okay, so my next value, so that was this guy moving across to here. Now let's do the pi on 2, so it's going to be pi on 2, take away pi on 3. Now this should be something that's positive. So this is the same as 3 pi on 6, take away 2 pi on 6, so it's pi on 6. So that value is in there, okay? And so we can kind of see, oh, it's kind of gross to be honest. It's going to be something like that. So it's going to be like that. It's going to be like that. It's going to be like this, like this, like this, and then it's going to actually continue going like over here somewhere, so outside the domain, but we don't need to draw that. So connecting this one up, comes down, back up this way, okay, and then through like this, back down, and this looks like a big mess. I'm sorry. Okay, it's something like that. It's what it's gonna look like. And we'll have a look in a moment. It doesn't look 100% right, but anyway. So the last thing is we've got this -2 out the front. So basically the negative is going to flip everything and the 2 is going to double it. Now the 2, we've already looked at this. The 2 is not going to affect it because basically what it's saying is, you know, take your old domains, your old, like it was only going up to 1. We're going to now stretch it out so it goes up to 2 in both directions. So up to +2, down to -2. But that does that in every single one of these cases. So if I draw a line going across in each one of these, you'll notice that it's going to, or attempt to, hit the 2 going across. So we can kind of ignore the 2 because we know it's doing that already. But the negative is the value that we need to look at. So we're currently sitting somewhere here. If I push it up to 2, it's going to be sitting up, you know, like somewhere like here. So somewhere over here. So my value is going to be coming down like this, okay? So the negative effectively flips this. So we'll use another color, we'll use purple. The negative flips this, it brings it down to this side, okay? And so it brings my function coming up like that. Now, I don't know about you guys, but there's only one of these functions that's actually doing anything remotely like that. Okay, there's only one of these functions that's sort of dipping down and coming back for that bottom bit. And I'm sure you guys can see this, but the answer in this case is going to be D. Okay, now, just to show that I'm not going insane, we're going to have a look at these. Okay, step by step. So we've got y is equal to, so y is equal to sine of x. Okay, we know what that looks like. It looks like this. Okay, then we go is y, well, I might leave it up there and we'll do another one. So y, so that's the regular one. Okay, now we do y sine of 2x. Okay, so as I said, it's sort of compressing in that sine wave. So where we would normally fit, so if I can try and fit 2 on, so where we would normally fit one of these purple sort of things, I don't know if you guys can see or not if I do this. So where we would normally fit one of these sine waves here, okay, we can actually fit 1 and 2, and that point should be the same as well. That's only with us just putting that 2x in, okay? Now, the next thing that we did is we replaced the So 2x, and it was a plus pi on 3. Okay, so that, as I said, you can see it shifted it all across. In fact, I think I was a little bit short. Okay. Anyway, it did shift it across a bit, so you can see where those points shifted across here. And then finally, the last one was when y is equal to sine, well, it was negative 2 sine, so negative 2, we said we're going to flip it and stretch it out. So of 2x plus pi on 3. Okay, so if I turn these other ones off, the difference between this one and this one is, well, effectively we've doubled it, so we've stretched it out. Okay, and then all of these values at the top have become all the values at the bottom, and it's basically just been flipped around the x-axis like that. Okay. Excuse me. Ugh. Alright, the discrete random variable x has the following probability distribution. So some probability, so basically think of it as if it's like an unfair dice. I roll it once, I get a 0, it's a quarter chance. A 1 is a 9 in 20 chance, a 2 is a 1 in 10 chance, a 3 is a 1 in 20 chance, and then a 6 is a 3 in 20 chance. Let mu be the mean of x. Find the probability that x is less than mu is. The probability x is less than mu. So, well, let's start off by finding what mu is. So mu, do it in red. So mu is our mean or our expected value. Okay. So what are we expecting to get in this experiment? What are we expecting to get? So one way that we can calculate our expected value is you take the score and you multiply it by its probability. So 0 times a quarter, plus 1 times 9 on 20, plus 2 times 1 on 10, plus 3 times 1 on 20, plus 6 times 3 on 20. Okay. 0 plus 9 on 20, plus 2 on 10, which is the same as 4 on 20, which I'll change in a moment. Plus 3 on 20, plus 18 on 20. I might change this one right now, just to make it easier. So what was that? It was 2 on 10, which was 4 on 20. Okay. So this, if I add it all up, it gives me 25, gives me 36 on 20, which is the same as, what's that? 1 and 16 on 20, which is the same as 1 and 8 on 10, which is the same as 1.8. I hope I've done that right, because 21, 22, 23, 24, 25, 25. It's 34, not 36. It helps if I can actually add up. So that's 7, and that's 1.7. So now we're looking for the probability of the scores when it's less than 1.7. Okay, so what are the ones where it's less than 1.7? Well, that's going to be this column here and this column here. So it's 1 over 4 plus 9 over 20. Okay, so because I'm looking for essentially the probability of 0 or 1, because those are the things that are less than the mean. So the probability of 0 or 1, so this is, so a quarter is the same as, what, 5 on 20 plus 9 on 20, which is 14 on 20. Okay, and so that's the probability of x being greater or less than 1.7, I should say. Cool. All right, that's the multiple choice done. 10 questions. Something that should take you 15 minutes in your exam. That took us 50, so that was pretty bad. But hopefully my explanations actually help you and explain why these answers are. Now, obviously, you don't have to sit there and explain it to someone when you're doing your exam. You just do it. But anyway, we're at that point where we've got some answers, so we can move on. All right. Student number in these boxes: 1, 2, 3, 4, 5, 6, 7, 8. Classic student numbers. Alrighty. Answer booklet 2, 90 marks. Oh, the big part. Alrighty. Using interval notation, state the domain and range of f of x. So f of x is a function that's drawn above. So my domain is the values of x that this function holds. So it starts at -1 but does not include it because it's an open circle. So we're starting at -1 with an open bracket. It goes all the way up to 4, and 4 is a closed bracket. So my domain is a closed bracket on the 4. So it's from -1 to 4 with an open bracket on -1, a closed bracket up to the 4. My range is the y value. So from what y value to what y value. Now it's from -4 up to 5. It includes the -4, so we put -4 in the closed bracket. We go up to 5. The 5 is open because it's an open circle at that point. So we put an open bracket for our range, and that is our domain and range. Now for you extension people at home who are following along, if you were to do the inverse of this function and were asked what the domain and range was of the inverse of the function, you literally swap them around. The domain becomes the range becomes the domain. It's a pretty cool little trick. Anyway, 2 marks for just getting those 2 questions correct. So that's pretty bloody awesome. Alrighty, Peter works in a restaurant and each customer can leave him a tip, some extra money. If you didn't know what a tip is, for good service. On one day, Peter earns 50 tips as shown in a cumulative histogram. One of the tips was incorrectly listed as $15 instead of $25. Giving reasons, explain what effect this would have on each of the following statistics. So the median and the mean. Okay. So, excuse me. Let's have a look at our little graph here, and we might make this a little cumulative graph just to make it a bit easier for us to deal with. Okay. Because this allows us to spot the mean, the median, and the quartiles a little bit quicker. Okay, just reusing this. So this goes all the way up to 50. So the median score out of my 50 values is going to be, so the median value, median number, it's going to be 50 plus 1 over 2. Quick little trick that will get you the number, which is 51 on 2, which is going to be 25 and a half. So the number that's between the 25th and the 26th score will be the number that gives it to you. So let's have a look. So it's 20, 22, 24, 26. So it's going to be whatever is in here. Okay. So it's this here. Okay, so basically what it's saying is, if we were to change the $15 to a $20, so we took a $15 out of here, okay, somewhere out of here, and we moved it up to here, what would actually happen? Well, this box would come down a little bit. Okay. This box would come down a little bit, and to compensate, this box would go up a little bit. And in fact, it wouldn't actually go up a little bit, it would stay where it is. It's just that this difference here, so this difference here, would be added on in here, okay? So you would actually notice that difference. So is that going to affect the middle at all? Is it going to affect the middle? Well, no, it's not actually going to affect the middle at all, because if we're not adding any new numbers in the $5 or taking in numbers from the $5, it's not going to affect that first half of the data, okay? And because this is cumulative, we don't care what position the $15 come in, okay, because we've just got them all in order. So the median, well, the median is not going to be affected, okay? So it's not going to be affected. Okay, so we'll still be at $15. It will still be at $15. Now the mean's a little bit different. The mean will actually change because if we add a little bit more on, the mean's actually going to change. Because if you think about what the mean is, we add up all the numbers. Every single number has something to do with this. It's not just the position of the numbers we care about, it's the actual numbers themselves. So the mean will change. Okay, the mean will change. because we do care about the value of the tip. Okay, so if I've got more $25 than $15, of course my average amount of tips is going to go up. The more I'm going to earn more money. Like, that just makes sense. So the mean's going to go up. The average amount of tip per person I'm going to get is going up. The median's not going to be as affected though. And it's why when we get into skewed data, so such as like positively and negatively skewed versus symmetrical, with symmetrical data we usually use the mean and standard deviations because they're not as affected by outliers. Sorry, they are affected by outliers. So when we have the normal distribution, that's what we're going to use. And the median range and interquartile range, mainly the interquartile range and median, is what we use when we have skewed data. Particularly when we have outliers, because the median is not going to be affected by those. It's also why if you're looking for a house in Sydney, that you would want to be looking at the median house price as opposed to the mean, because that one house that costs $15 million is going to massively affect the price of the others. Alright, Sarita opens an annuity account which requires contributions to be made at the end of each period. The table below shows the future of the annuity for $1 of various interest rates per period. So here's a table. We've got some periods, so 2, 6, 12, and 24, so some odd periods. But anyway, and basically for every $1 you put in, depending on your interest rate of what it is, this is what you're going to get out. So if you would put in $10, okay, in a interest account or in an annuity over 2 years or 2 terms at 1.5%, you'd multiply your $10 by 2.015, and that would give you how much money you'd get at the end. Now, to save for a computer for university, Sarita makes regular deposits at the end of each month into an annuity that pays 3% per annum. The annuity compounds interest monthly, and how much would Sarita have to deposit each month if she expects the computer to cost $2,800 at the end of 2 years? Whew, that's a mouthful. Okay, so it's monthly. Okay, so we've got 3% per annum. That's going to become, we're going to change it to per month. We're going to divide that by 12, and we're going to get 0.25% per month. Okay. Now, her 2 years that she's going to be doing this for, of course, because she's doing it per like a monthly thing, her 2 years is going to equal to 24 months. And okay, so let's go from there. So she's in the 3%, so the 0.25% per month, and for the 24 months. So let's go up and have a look. So it's 0.25 for 24. So the magic number that we're going to be looking at is 24.7028. Now, the amount that she needs to borrow is $2,800. So we go $2,800. And because we're trying to find the amount that she needs, the exact amount she's going to be paying, okay, normally we would multiply it by the thing and then work it out. But because we're trying to work out how much she's going to be paying back per month, okay, we're going back per month. We're going to divide this by the 24.7028. Okay, so when we do this, we get the value 2800 over 24.7028, and we get $113.35. Okay, and this is basically the amount of money she's going to be having to pay back each time, which is pretty cool, I think. So it's not too much, but for 24 months, like 2 years, is a long time. It's probably better just to save up for it, and you don't have to pay any interest whatsoever. Because if we actually had a look at it, 28,000 divided by 24, she just saved up less. Oh, because she's putting 113 into a savings account, right. So if she was just to save up the raw amount, the savings is actually saving her a little bit of money. So yeah, that makes sense. Okay, I thought she was like putting into a loan, but no, it's into an account that's compounding. It's working out interest, and then she's putting a little bit more in each time. Okay. All right, some calculus. All right, sick of the money. Let's do some calculus. So we've got differentiate e to the x sine x. Oh, this is quite gross. It's a function of a function, and it is a product rule as well, because we've got a product of two functions. We've got x times sine x. So we might start by trying to get rid of, or by trying to deal with this power. So when we differentiate exponential terms, so e to the f of x, the derivative is just the derivative of the function that's up the top times e of the original function. So if my function is equal to x sine x, okay, we need to use the product rule to simplify this essentially. So let's have a look. So u dash, v dash. I'm not too sure what your teachers use, what notation they use, but I just use u dash, v dash. So it's called ux and v sine x. So u dash is 1 and v dash is cos x. Okay, and the product rule says that f dash of x is going to be equal to uv dash plus vu dash, or vu dash plus uv dash. Doesn't matter which way we do these ones. You can add it left to right or right to left. It's up to you. It's completely up to you in this case. But anyway, actually doing these ones, substituting these values in now, they are u and v dash, and now v and u dash. So u and v dash is x and cos x, and plus v u dash. So u dash is 1, v dash is sine x, so it's just going to be sine x in that case. Okay, then substituting it back up into this thing, y dash is f dash of x times e to the f of x. So f dash of x is x cos x plus sine x. Okay. E to the, and then the original function again. So e sine x. And that's it. Okay, pretty straightforward. So it, like, the exponential functions don't change. It's always the derivative at the top comes out. And the only thing that we had to do in this particular case was work out what the derivative of that, well, what the product rule, like use the product rule to find the derivative of that big disgusting gross guy was. Anyway, let's continue. Question 15, okay, if f of x is equal to log e x squared plus 1, calculate the derivative at -1. Alright, so we should probably find derivative. Now, logarithm derivatives. So this is just knowing your derivatives, and these are on your formula sheet as well. So on your reference sheet, if you look on your reference sheet, you'll actually have these formulas and they'll tell you what to do. But if you have some function of y being equal to a logarithm, then the derivative is going to become the derivative of the inside function over the original inside function, okay? And that's all it is, okay? So the classic one, of course, being log e of x turning into 1 over x, because the derivative of x is 1 over the original function being x, okay? And that's pretty much why log e of x turns into 1 over x. But don't do that when you have something like this. We'll talk about that later. Don't remember that. Ignore that. Scrub that from your memories. Okay, so my function in this case is x squared plus 1. So f of x is equal to x squared plus 1. Okay, so y dash, or f of x dash. Hang on, let me do it this way. So f of x is equal to log e of x squared plus 1. So f dash of x is going to be equal to, so it's the inside function. Wow, that's not what I wanted. It's the inside function on the bottom. So x squared plus 1 goes on the bottom. On the top is the derivative of that bottom function. So the derivative of x squared plus 1, well, the plus 1 term disappears. The derivative of x squared is just 2x. And that's our whole answer. Now, we're not finished yet though, because we're asked what's the value at -1. So what's the derivative value at -1? Well, that's quite easy. We can substitute it into this and hopefully get an answer. So 2 lots of -1 over -1 squared plus 1. It's really important that you put the -1 in brackets before you square it, especially if you're using your calculator to do this. Now, being in advanced, you shouldn't have to use your calculator to do that because we should know that -1 times -1 is equal to 1. However, make sure you do brackets, because if I quickly just go -1 squared, watch what happens. We know that's not true because -1 times -1, it's two negatives. They make a positive. Because what your calculator does, it says, well, it sees this bit first. It says, okay, let's do the 1 squared and then put the minus on the top. Okay. Anyway, as a little side note, it's going to be -2 over 1 plus 1, which is just 2. So my answer is equal to -1, and that's it. So very straightforward little logarithm. Might have to have a drink break in a moment because my drink is all out and my throat is on fire, but nonetheless, we'll continue. Alrighty, a shop assistant is building a display of soup cans. The top row will contain 3 cans and each subsequent row will have 2 more cans in the previous row. How many cans will be in the 10th row? Well, believe it or not, this is actually an arithmetic series, okay? Well, if you think about it, we're starting with 2. Not 2, sorry, we're starting with 3. And in each sequence, we're adding 2 more. So it's plus 5. Well, sorry, not plus. It's going to be 3 on the first one, and then 5. And then 7, because we're adding 2 more. And then 9, 11, etc. Okay, so this is an arithmetic series where our A value, our starting value is 3, and our difference is 2. Now we want to know what or how many cans will be in the 10th row. That is, what the number is in the 10th row. What number is in the 10th row. Okay. So we're looking for T of 10. Now again, this is a formula that is on your reference sheet. But if you don't quite remember that, it's okay. The formula is A plus, and it's N minus 1 times D. Okay. Now we just need to substitute our values in. So we know our N value is 10 because that's the position that we're trying to find. Our A value is our beginning term, which is the 3. Our difference is 2 because it's going up by 2 in each jump. So substitute these values in. Okay, we get 3 plus, and it's going to be 10 minus 1 times 2, which is the same as 3 plus 9 times 2, which is 21. Because 9 times 2 is 18 plus 3 is 21. So the 10th row will have 21 cans. And that's pretty much it, okay, for that bit. Now the shop assistant has 400 cans. How many rows is the tallest display that he can use building this pattern? So essentially we know what the sum is now. So we actually know that the sum of this sequence is equal to 400 because the total amount of cans he's got, the sum of the cans, is equal to 400. Now we need to work backwards to work out what our N value is going to be, okay? So again, what do we know about this? It's the same sequence, so we know that our A value is 3 and our D value is 2. Okay, so we know these few things. Let's substitute them into the SN formula. Now again, this formula is on your reference sheet and it looks like, which one do I want to use? Well, we don't know what's in the last position, so we're going to have to use this formula. Sn is equal to n on 2 lots of 2a plus n minus 1 times d. Okay. Now we know S of n is equal to 400. Now we don't know what our n value is. This is what we're trying to find, so we're going to leave that as an n, and we can put that in our shopping list of things if we like. N is equal to question mark because we don't know yet. Okay, times, and this is just a bigger bracket. Okay, don't be scared by the square brackets. It's just another bracket. So 2 times a, which is 6, plus, because it's 2 times 3, plus n minus 1 times d. So my n value, again, I don't know. I'm just going to substitute that in. But my d value in this case is equal to 2. All right, so solving this equation from here. Okay, well, let's simplify it a little bit. We'll expand those brackets. I'm going to get 400 is equal to n on 2, lots of 6, plus 2n minus 2. Okay, simplifying a bit, I'm going to get 400 is equal to n on 2, 4 plus 2n. Okay, and we could expand the brackets from this point, and in fact, that's what we're going to do. Now, how am I going to do this is I'm going to remove this 2 first. Okay, this is just an n over 2. It's like a fraction. It's currently dividing the right-hand side by 2. So to get rid of it, I'm going to multiply both sides by 2. I'm going to get 800 is equal to n. Lots of 4 plus 2n, which means that we have 800 is equal to 4n plus 2n squared. Now, I'm hoping some alarm bells are going off at the moment, because if I rearrange this, what we get is we get a quadratic equation that we can solve. Okay. Now, I don't know what the solutions are to these numbers. It's quite big and quite scary. What I'm going to do is I'm going to use the quadratic formula to get an answer. So this thing, so n is equal to, so we'll write it out, negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. So n is equal to negative b, so negative, so the b value is the 4, plus or minus 16 minus 4 times a, which is 2 times c, which is negative 800. Talk about convenient number, over 2 times 2. Now, substituting this into your calculator, or putting this into calculator, so minus 4, so we've got to do this twice. So we're going to do the plus part first, so plus 16 minus 4 times 2 times negative 800 over 2 times 2, which is 4. Whoops, over 2 times 2, which is 4. And we get minus 1 plus the square root of 401, because I know what that is. 19.02. And we need our other value as well. So n can equal to that, or n could be equal to, so we do the negative version. Well, this is going to be something really, really small. Okay. So obviously we can't have negative 21 rows, and because it's because it's 19.02 rows, okay, where the question, think back to what the original question was asking, okay, how many rows can we make of cans? Well, we can create 19 and a little bit rows. We'll have some stuff left over, but how many rows is that actually going to make? Well, 19 rows is how many? Okay, and that's how many we're going to make there. Now, I'm going to skip this one because it's to do with the normal distribution, and I haven't actually done normal distribution yet, which, like, personally, I haven't done it yet because it's only one of the new content, and this is the first year that I'm actually teaching this course. So we're actually currently doing that topic at the moment. So I'm going to skip this one for now, and at some point we'll come back and look at this one. Possibly. Probably not really, but you know, if you're sticking around for the statistics, I apologize. We're just not quite up to that point yet. But I'm sure you've got amazing teachers out there who can help you with your own statistics problems. So we'll move on from that one. We'll go straight down to this one. All right, the function, excuse me, the function f of x is equal to x minus 1 squared is transformed, and the equation of the new function is of the form y is equal to k of f of x plus a plus c, where k, a, and c are constants. The graph of the new function is shown below. What is the values of k, a, and c? Well. We've got a. We have a, or we have here a quadratic, a parabola. Okay. And we know it's a parabola because it's a going up a parabolary. Now, let's have a look at this original function they've given us. The function x minus 1 squared is transformed into this thing that they've drawn for us. So let's draw that original function, see what it would look like. Now, it's annoying because the scale is kind of whack, but the minimum turning point, or the local minimum, or the stationary point, if you will, is going to be at x is equal to 1 because it's a double root. Okay, so if you've done extension 1 maths, you'll know what a double root is, or you should know what a double root is. But basically, if I was to expand this, x minus 1, the only zeros where this occurs is when x is equal to 1. So there's only one point when this thing touches. Otherwise, this function goes up from there. Okay. So a normal parabola, 1, 2, 3, 4. Okay, it goes across 1, up 1, and then it goes across 1 more, and then it's going to go up 3. Because if you think about a regular parabola, you square a number, okay? You take a number, you square it. So if you take the number 0, you square it, you get 0, okay? If you take the number 1 and you square it, you get 1. If you take number 2 and you square it, you're going to get 4. So it's going to up, well, exponentially, almost exponentially. It's going up, it's growing quite rapidly. That's what I was looking for. So what we're going to do is we're going to compare this function here, which is our y is equal to f of x, with the function that we've been given. So how are we going to do that? Well, we know that this function has been shifted up, okay? How much has it been shifted up by? Well, it's moved from 0 up to 3. So this value here at the end is going to be 3 because this whole thing has been shifted up by a factor of 3. So my c value is equal to 3. That's an easy one. It's just how far up or down it's moved, and that doesn't rely on anything. Now the next value we're going to be looking at is our which one should we look at next? Maybe our Oh my god, I've drawn the wrong bloody graph. Holy dooly. Actually helps if you draw the right graph, guys. So, just saying, draw the right graph first, and then do the answer. So, x is minus 1, the only values for where this thing, or the zeros for this thing is when it's at x is equal to 1, not negative 1, of course. That makes sense, because that will give us an a value in here for how far it's moved. So our a value, okay, so we're going to be replacing our x with x to x minus 1. So it's going to be, well, from x minus 1 to our new thing. So it's going to be, so how far have we moved across? We've moved across 1, we've moved across 2, so it's going to be x to x minus 2. Okay, so if we substitute that into this, our a value is going to be equal to, it should be equal to 2, I would imagine, because we're moving it 2 to the left. So our a value is 2. Yeah, because we're going from negative 1 to 1, so we're going across by 2. Okay, so we've got our two values. So because we're translating left by 2, a is going to be equal to 2. Okay, and is it 2 or negative 2? Let me think. Left 2 places, so it's going to be a is equal to 2, yeah. Because if I was moving it more to the right, it'd be a negative value that we're going to be substituting in there. Yeah, okay, cool. And then the translation up by, and we've moved it up by, well, we decided it was going up by a 3. So that means our C value is equal to 3. Okay, so if we substitute these into our original or into our new function, we've got y is equal to k f of x, and it's going to be f of x let me think. It's going to be k f of x, oh, sorry, not k f of x, it's going to be k of, so my function is x minus 1, so it's going to become x plus 1 squared plus 3. Yep, that makes more sense. Okay, and we need to know a new point that satisfies this. So it's going to go through the point, so it goes through 0, 5. So if we substitute this in, so 5 is equal to k lots of 0 plus 1 squared plus 3. So 2 is equal to k lots of 1 squared, or 2 is equal to k. So therefore, a is equal to 2, c is equal to 3, k is equal to 2, and therefore the function, so the new function, y is equal to, it's going to be 2, lots of f of 2x, or x plus 2. Yeah, because we're moving to the left 2 from the original. Yep. X plus 2, and then it's going to be plus 3 because it goes up 3. Cool. And there we go. So that's our new function. Alrighty. We might do 19, and then we might do 20, and then I think that we might call it, and that might finish this up for tonight. And then tomorrow, or another time, we might continue on with 21, because we've done it for an hour and a half already, which is a pretty good effort. But yeah, anyway, let's do 19 and 20. Okay, two events, A and B, such that the probability of A is 3/5 and the probability of B is 1/4. If A dash denotes the complement of A, calculate the probability of A dash and B. So we know that the probability of A dash is going to be equal to 2/5. We know the probability of B dash is going to be equal to 3/4. Okay, so we know these two things. We know these two facts. Now, we want A or B. Now, there's a formula that we've got, and the formula is the probability of A. Now, I'm going to get this the right way. A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Okay? So we can put in the information that we know to work this out. So, So, if A dash denotes the complement of A, calculate probability of A dash on B. Probability of A dash on B. So it's going to be the probability of A plus the probability of B plus the probability of A and B. A and B, A and B. Okay, let's have a look at a little Venn diagram, I think, would be in order. So for this particular, actually, I'm going to do it as a two-way table. I think a two-way table might help a bit more. So you've got A, and you've got not A, and you've got B, and you've got not B, okay? And you've got your totals, of course. Now, we know the probability of A is going to be 3/5. So it means it's 2/5 here, and it's going to be 1 here. And we know that this one's going to be 3/4, and we know that this one down here is going to be a quarter. No, I've got that the wrong way around. It's going to be a quarter up here, because the probability of all of B is a quarter. The probability of that is 3/4. Now we know the probability of A or B. So the probability that A or B occurs is 3/4. So the opposite of the probability of A or B would be the probability of A of not A or not B. So basically it'd be this guy here. So if it's 3/4 for everything, then it's going to be 1/4 for the things that we're missing out on. Okay, and the other things are going to have to add up to 3/4. So it's essentially going to be like a quarter, a quarter, a quarter, but obviously not like that. So this one and this one we can work out now. We know this one needs to be 2/4, okay, because it's 2/4 plus a quarter makes 3/4. Okay, and we can work out this one now because it's going to be 3/5 take away 2/4, which is equal to something over 20. It's going to be 12 take away 10, which is 2 over 20, which is equal to 1/10. So this is 1/10 in here, and that just makes the other value gross. I feel like this is a lot of work for a 1 marker. There must be something I'm missing. Anyway, we're filling it out. We're filling out the two-way table. It's fine. 1/10 plus what is a quarter, or a quarter plus 2/5. Oh, so we'll go this way. 2/5 take away a quarter is the same as over 20. It's going to be 4 take away. It's going to be 8 take away 5, which is going to be 3 over 20. So it's 3 over 20 now. Now, excuse me. So the probability of A or B is 3/4. The probability of A is 3/5. Not A and B. So not A and B is that box in there. Okay, there we go. That was easy. So 3 out of 20. Okay, A and B are mutually exclusive. So basically in this one, we were just looking for where the overlap was. That's what it boiled down to. So where was that overlap in the two-way table? Okay, so A and B are mutually exclusive. So if A and B are mutually exclusive, that means they've got nothing in common, okay? So if I was to do my two-way table again quickly, I love two-way tables, it makes it probably much easier. Okay, it means that this thing up here is going to be 0. And we already know that this is going to be 3/5, and this is going to be a quarter. So that means that this has to be a quarter, and this has to be 3/5, okay? So A, B, not A, not B. And we want to find when it's not A and B, so we need to find this thing here. So it's just going to be a quarter again. So that's nice and easy. Much an easier one that time around. So two-way tables to the rescue that time. Yeah, the solution they give is 5 out of 20, which is also a quarter. So pretty straightforward. So if there's nothing, there's nothing in common, then A dash and B are the same thing. Like, well, no, because that's not including things that are left out. But in this case, you know, like A dash, yeah, like it's mutually exclusive, so they're not including each other. Anyway, 1/4, happy with that. Let's do number 20. Okay, last sit. Okay. Given the function g of x is equal to this monstrosity, it's 3 over 2x minus 1 plus 1. Okay, what we're going to do is going to find a vertical asymptote. Now, vertical asymptotes are basically where the function doesn't work. So when does the function not work? So it's a fraction. So when does the fraction not work? It's when the denominator doesn't work. So if you said denominator doesn't work, go you. So when does the denominator not work for this? Well, the denominator doesn't work for this when x is equal to, well, when that whole bottom is equal to 0. So in other words, it's when 2x minus 1 is equal to 0. Or when 2x is equal to 1, or when x is equal to a half. Okay, and that's it. That's all you need to do for that bit. So there's a vertical asymptote at x is equal to a half. So sketch the function g of x, showing in the space below, labeling the asymptotes and the intercepts. All right, so well, we just decided that there was a vertical asymptote. I'm guessing that's why they set us up with that first question. So we could draw our vertical asymptote at x is equal to a half. Now, when you're doing your vertical asymptotes or horizontal asymptotes in that fact, make sure you do a dotted line and try and make it as straight as possible. Like mine's okay, but you can definitely do it straighter. Now, this is well, we found where the vertical asymptote is, but we need to also check if there's any horizontal asymptotes as well. Now, the easiest way to check if there's any horizontal asymptotes is to substitute something really big into this equation. So check horizontal asymptotes. Let x be equal to something big, like 10,000. And whatever y is, it's going to tend towards whatever the asymptote is. What it goes towards is going to be asymptote. And this is a little trick that allows you to find an asymptote, a horizontal asymptote that is, really, really quickly. So 10,000, put that into the calculator. Minus one's going to make such a difference. And look at that. It goes towards 1, which coincidentally is that number that's sitting up there. So there's also a horizontal asymptote at y is equal to 1. Now, I don't know about you guys, but I know what this shape is. The shape of this graph that we're about to do. It's a hyperbole, or hyperbola. Okay, so we will need the 4 quadrants to do this. Okay. Now, the easiest way to do this is to essentially say to ourselves, okay, well, what happens when we get really big or really close? So I substituted in a really big number, so 10,000's all the way over here somewhere, and it got really, really bloody close to 1. So my dot's somewhere down here, okay? Now, I'm just going to add in some stuff, like the x is equal to a half for the asymptote, and the y is equal to 1 for that asymptote as well. Okay, so make sure when you're sketching your graph, you're adding in the extra components as well, like you're actually putting in things. Okay, so for this hyperbole, we're going to either have something here, 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 or here, depending on what type of hyperbole it is. Now, because it is a positive hyperbole, that means we're going to have something in this one and this one. If it was negative, then it'd be flipped. That's just something that you will need to remember. You can also test it by just chucking in some numbers and seeing what you get. So if I put in, say, the number like 4, okay, let's put the number 4 in. What do I get? I get 10 on 7, which is 1.4. So it's like, what, somewhere like here, okay? Now you could just put a bunch of numbers in, but I'm going to put in big numbers and small numbers and numbers really close to asymptotes to see what happens. So as we did before, we put in a big number, say 100, and we got something really close to 1. So basically this function starts off very, very small, and it's going to slowly come closer and closer. It's going to grow and grow the closer it gets to 0, or to half in this case. So obviously we can't put half into this, because if I try to, I get a math error because it doesn't work. So let's try something else instead. Let's try something that's really close to a half, and let's try 0.40001. Okay, oh, and would you look at that, something really big. So numbers that are really close to it are very, 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 very positive. So it's going to come down like this, okay? So let's just substitute another number in, let's say the number 2, okay, to sort of see whereabouts this number's going to go. So 2 is equal to 2, so it goes about there. Let's put in 3. Okay, 3 is about 8/5, which is about 1.6, so it's going to be a bit lower. And then if I dare say if I substitute 5 into this, if I substitute a 1 into this, it's going to be a bit higher, and 1 is 4, so it's like up here. So yeah, it's going to be something like this is what our hyperbola is going to look like. So something like that. Okay, so this is the top right hand bit. Now there's no intercepts that we need to plot because it doesn't cut through anything, so we can just leave this one as it stands. Now, onto the bottom half. So, very, very, very small number. So let's try, negative 10,000. That's or 1,000, that's very small. If you look at that, it's very, very close to 1, so it's going to start off somewhere like up here. Okay, let's try something very close to 1, but from the opposite side, from the negative side. So like 0.9. Oh, would you look at that? It's really, really, really close to 4. Oh, it's not 1. I need half. Huh. That would probably help. So half. So what's close to half? 49999. Oh, look, it's really big. So it's going to be somewhere down here. Now we need to know where my x and my y intercepts are. So my x-intercepts occur, my y-intercepts occur when x is equal to 0, so it's at -2. Okay. So y int at x is equal to 2. -2 even. And we need to also, because it's going to come somewhere through here as well, so that it can shoot up close to that guy there, we need to work out what the x-intercept is going to be as well. So the x-intercept is going to be, how are we going to work that one out quickly? The x-intercept, so when is this thing equal to 0? So what value? Well, it's when the whole function is equal to 0. So it's going to be, so what number do I need to substitute in to make this equal to 0? So what, so what number do I need to substitute in to make this whole thing equal to 0? Or when do I need to make this left-hand side equal to 0? Okay, so, or -1 it should be. So how do I make this -1? Well, I need to make this bottom equal to the bottom needs to be equal to -3. So I need that to be equal to -1. Beautiful. So -1 is my x-intercept. And then we connect these up. Now, when you guys do your exams, we're not looking for Picassos, or I hope not anyway. Because if you are doing Picassos, you probably should have done art and not maths. But, well, I mean, you could do both, and there's no discrimination here. In fact, there's some cool looking maths things in art. Which pop up. But regardless, yeah, so we're not looking for, like, the point is, we're not looking for excellent drawings. The main thing we're looking for are something that looks relatively close to what you're meant to be drawing, and we're looking for the intercepts and the equations of the equation of the asymptotes. Oh my god, I'm so dumb. It must be getting late. Alright, so that's number 2. Part 2 done. Alright, let's finish this off. Let's do part 3, and then that might finish this up for tonight, and we'll finish off the rest at some other point. Alright, the function g of x was derived from applying transformations to the function... God, it's more transformations. What was the horizontal translation applied to achieve this transformation? Okay, so it's only a 1 marker, so we only have to write one thing. Okay, so a horizontal translation is affecting the x values. Okay, so it's either pushing it in or it's pulling it out from the x. Okay, so it's going to be something to do with the x. So what's occurring on the x? Let's have a look back up at our function. Okay. The x is being affected by a factor of 2, okay? Now, wait, what's the question? Oh, translation. I'm thinking of dilation. Okay, so it's the thing that's being affected by the x. So if I look at the bottom of my function where the x is occurring, okay, it's down here, okay. X is down there, so it's 2x minus 1, okay. So I want to know what's happening to that x specifically. So let's pull out a factor of 2 in this case. So this is the same as 2 on x minus a half, okay? And if you look at this, okay, the half here, the minus half, is telling you how much it's moving. In this case, it's moving to the right, okay? So it's moving to the right. By a factor of a half, okay? Now, the reason why it's not moving by a factor of 1 is because we want to pull out, we want to know what x minus k is, okay? We want it when it's x minus k. We don't want it when it's 2x minus k. We want it when it's x minus like whatever the value is. And to do that, you just pull that common factor of 2 out, okay? And you get that. What do you reckon? Should we call it there? Should that be the end of this live stream, do you think? Should we call it there, or should we maybe crack on with one more? Do 21. What do you think? We could do 21. What do we got? Oh, it's an integration problem. We've got 2 integration problems. I'll tell you what, let's treat ourselves. Let's do some integration, and then we'll call it. Very hard to stop once I get started, that's for sure. Yeah, just 2 integration problems. All right, we'll do these 2 integration problems, and that'll do us. Okay, so find the integral of this. Now, it's 24 lots of 2x minus 7 to the power of 5. Now, when we go to integrate something like this function here, think about what you're doing when you're differentiating something like this. So if I was to say differentiate this function, the same function, so 2x minus 7 to the power of 5, okay, what would you do? Because remember, integration is just the opposite of differentiating. Hopefully what you are thinking is that you bring the power down the front, so 24 times 5, times the derivative of the inside, so 2, and then it's the original function of the inside, and then 1 off the power, okay? So differentiating, you do that. So you bring it all out, and you take 1 off the power. Well, when we're integrating, we actually, kind of think of it like pulling it back on the inside, okay? So we're bringing numbers from the outside and pulling them back in on the inside, or taking factors of the outside and pulling them back on the inside, okay? A lot of the time, they don't actually give you a number to work with, but in this case, they've given us 24, so it makes it a little bit easier. So let's think about what would happen if we were to do the opposite. So I would need I pulled out the derivative from the inside to the outside. So I would need the derivative of the inside to bring it back in. So the derivative of the inside is equal to 2. Okay, so the derivative of this, is 2. So I need to divide this whole function, or at least this guy here, by 2. Okay, and that gives me my first bit. Okay. Now I need to do this guy up here, this power of 5. So what would normally happen is I would subtract 1 and times by the old power. But the opposite of that is so timesing by the old power, the opposite would be dividing by the new power. And so the new power is going to be 6. So I need to divide that by 6. So what we end up with is 24, okay, and this is going to become, so it's going to be 24 on 6 times 2, which is 12, lots of 2x minus 7 to the power of 6, okay, which is equal to 2 lots of 2x minus 7 to the power of 6. And that's it, that's the whole thing. So it's basically doing the opposite. So think about what you would do to differentiate it, and then do the opposites. So you would subtract 1 from the power and bring the power down. You'd multiply by the old power. So multiply by the, subtract 1, multiply by the old. So the opposite is to divide by the new, multiply by the old, divide by the new, and derivative times by the derivative, divide by the derivative, okay? So the derivative in that case being 2. So we're dividing by the derivative of 2. Okay, and that's it, it's pretty straightforward. Ooh, what do we got going on here? We've got 2x plus 2 over 4x squared plus 8x plus 1. Oh, how are we going to do this? Well, it's not as hard as you may think. Okay, it involves a little bit of algebraic manipulation. Okay. So, let's have a quick look at what we can do. Let's let y be equal to 4x squared plus 8x plus 1. Now, as soon as you see a fraction with integration, so remember back up here, we did some derivatives. So we did some derivatives up here, okay, and we did some derivatives. And we got a fraction as one of our answers. So we'll quickly go find it because it's really useful. Here, we've got a fraction as one of our derivatives. Remember, the integration is the opposite way, is doing the opposite thing. So if we have a fraction, we're hoping to get it back into something that looks like a logarithm. Now to do it, we need the derivative of the bottom on the top. So let's go back down to our function in this question and have a look. Do we have the derivative of the bottom on the top? Okay. Well, what is the derivative of the bottom? The derivative of the bottom is 8x plus 8. So straight up you're thinking, well, no, we don't. We're actually missing out by a factor of 4, which is a shame because that would be really, really useful. But there's a little trick that we can do to get that factor of 8 on top, okay? What do I need to multiply 2 by to get to 8? Well, hopefully, that one didn't break the brain cells too much, and I need to multiply it by 4. So if I multiply the top of this function by 4, okay, I should end up with 8x plus 8, okay, which is what I want. So multiplying it by 4, I get 8x plus 8. But I can't just multiply a whole function by 4 because it changes the question, like it completely changes the question. It'd be convenient if I could do that, but it completely changes the question. I can, however, manipulate it in a way so that I haven't actually changed it. So I've included the 4, but I haven't actually changed it. The way I do it is by once I put this 4 out the front, okay, I also need to compensate by multiplying it by a quarter. And I can multiply the whole integral by a quarter. Because it's a quarter and 4, if I multiply those two things together, I end up with 1. And if I multiply my original integral by 1, well, that doesn't, I don't care about that because it's just equal to the original integral. This is just a way that I can break it up so that I got the derivative of the bottom on the top. So I can rewrite my integral. So this is 2x plus 2 over 4x squared plus 8x plus 1 dx. I can rewrite this as a quarter of 8x plus 8 over 4x squared plus 8x plus 1 dx, okay? Now, because I've got the derivative of the bottom on the top, we can just transform this straight into a logarithm. And it's going to be log base e of my function, which is 4x squared plus 8x plus 1. It has to be that original function. Okay, and it's a quarter of that original function, okay? So it's a quarter of that original function, and we're multiplying it by like that. And so that's it. That's the whole answer. Okay, so a lot of little, it's like a little trick to get that answer, but it's something that we can do, and it's something that you can do to answer. Make sure you put it in absolute values too, because we know that we can't have a negative logarithm, and that would break maths forever and ever. And that would be a shame, because then I would be out of a job. So, with that being said, I think I might call it there tonight. We might continue this on another night. Okay, I do have it saved so that we can go through it again, and do it later, later at a later date. But I hope this has helped in some way. Just, as I said, just as another voice mainly for you guys, so that you know, or that you have that another voice, just to give you a hand with something with these tough times that are coming up, with your exams that are coming up, especially too, if you are sitting your exams, if we do eventually sit our exams. As I said, it would be a shame if you're putting in all this effort and we don't sit our exams, but there's nothing that we can do about it. We can just only prepare only prepare for what we know, and this is all we know at this time. So yeah. So with that being said, I might leave it at this, guys. I hope you have appreciated this, and please hit the subscribe if you want more of this, because it does make it easier for me to see that there is a demand for this sort of stuff out there. And please do make sure, if you tune in again, ask questions if you do have them, because I'm happy to answer. Obviously, I've had a pretty blank chat tonight, but I know these videos do get played back a little bit. You know, my other one that I did ended up getting 600 or so views at this time of recording, which was pretty awesome. But you know, it's just a different HSC trial to have a go at. And yeah, if you want any other help or stuff too, just give us a shout, and we'll go from there. Alright, thanks guys, I appreciate that, and enjoy the rest of your night.